Today, let's talk about the famous integration technique, Feynman's technique or Feynman's trick. Given a difficult integral from a to b of x dx, the idea is to artificially introduce a second variable t to create a new function, still denoted as of x and t, if it is nicely behaved. For example, it is continuous with continuous partial derivative. Then we can use the rule called differentiation under the integral sign. It is d over dt integral from a to b of xt dx equals integral from a to b partial t of x t dx. We use partial derivative because the function has two variables, right? So we denote that as star. We do this one to hope the integral on the right side could be easier to integrate. Before moving on, we have to say the rigorous statement of conditions for the rule star needs some concepts from real analysis or measure theory. Today, we don't want to talk about that, but all the functions in the following two examples are nicely behaved, so the rule star can be applied. Now, let's look at the first example. So we consider the integral I equals from 0 to 1 x cubed minus 1 over ln x dx. If you use the traditional methods like integration by parts or substitution, it is very difficult to integrate. The difficulty lies in the fact the bottom is the ln function. If we can cancel the ln function, that would be much easier to integrate. But how can we create ln function? Exponential function, right? We know x to the power t, if viewed as function t, take derivative, we know it equals x to the power t ln x. Based on this observation, let's introduce a new function it equals integral from 0 to 1 x to the power t, replace cube, minus 1 over ln x dx. We assume t is greater than or equal 0. First, you can see if t equals 3, that's our target integral. So we get I as 3 equals I. When x equals 0, when t equals 0, x to the power 0, 1 minus 1, 0. So we know I at 0 equals 0. Now apply the rule, right? Take derivative with respect to t. The left side is I prime t. The right side, integral from 0 to 1 partial t. The function integrand is x to the power t minus 1 over ln x dx. Be careful. At this moment, t is the only variable for the differentiation. So we get integral from 0 to 1. The derivative of x to the power t is x to the power t times ln x. The derivative 1, 0. The bottom's ln x dx. We cancel ln x, so we get integral from 0 to 1 x to the power t dx. We know the variable of integration is x. So there's a power function. We know the antiderivative. It is x to the power t plus 1 over t plus 1. Then evaluate at 1 and 0. When x equals 1, we get 1 over t plus 1. When x equals 0, just 0, right? So then we get I prime t equals 1 over t plus 1. To recover it, we integrate both sides with respect to t. So the left side just it, the right side integral 1 over t plus 1 dt. We know the antiderivative. It is ln absolute value t plus 1 plus c. To figure out the value of c, we let t equals 0. We know when t equals 0, I equals 0. So 0 equals I at 0. But when t equals 0, this part equals ln 1 plus c. Ln 1 equals 0. So we get c equals 0. So we get the expression for it without integral. It equals ln absolute t plus 1, right? So our target I equals I when t equals 3. Plug in t 3 plus 1, 4. So we get ln 4. Next, we consider our final example. It is a famous Gaussian integral. Very important to probability theory. And we know the value is square root of pi. A standard way to calculate the integral is to square the integral to create double integral, and then using polar coordinate. Now let's apply Feynman's technique to calculate the integral. First, notice that the integrand is an even function, so we can write it as 2 times 0 to infinity e to the power of negative x squared dx. Let's denote I as the integral from 0 to infinity e to the power of negative x squared dx. You can expect the value be square root of pi over 2, right? But how can we create the value pi? Oh, we know inverse tan. You know, arctan at infinity equals pi over 2. And we also know the derivative of arctan equals 1 over 1 plus x squared. Based on this observation, we can introduce a new function, jt equals 0 to infinity. The bottom is 1 plus x squared. To potentially cancel the bottom, let's write the top as e to the power of negative t squared times 1 plus x squared dx. T is greater than or equal 0. Now let's apply the rule star d with respect to t. So the left side just j prime t, the right side equals from 0 to infinity partial derivative e to the power of negative t squared 1 plus x squared over 1 plus x squared dx. Be careful. At that moment, t is the only variable for the differentiation. So we get integral from 0 to infinity. The top is e to the power of negative t squared times 1 plus x squared times the derivative of the exponent, right? So it is negative 2t times 1 plus x squared over the bottom 1 plus x squared dx. Now we can cancel 1 plus x squared, right? So we get integral from 0 to infinity. Actually, we can also take the factor negative 2t out. Yeah, so let's take the factor negative 2t out 0 to infinity, and also break the exponent to e to the power of negative t squared times e to the power of negative t times x squared dx. Now let's take out this factor too. So we get negative 2t e to the power of negative t squared times integral from 0 to infinity e to the power of negative tx squared dx. At this point, let's do a substitution. Let u equals tx. So u equals tx. Then you see du equals t times dx, right? So we get negative 2t e to the power of negative t squared. And when t greater than 0, if x equals 0, u equals 0. X equals infinity, u equals infinity, right? And the integram becomes e to the power of negative u squared, and dx equals du over t, right? We cancel t, and you see we get negative 2 e to the power of negative t squared. And the remaining part, if you want, you can change u to x. So exactly the target integral, I. So at this point, we get the derivative of jt equals negative 2 e to the power of negative t squared times I. The next key step would be integrate both sides from 0 to infinity. So we integrate both sides from 0 to infinity dt, right? So then the left side is integral 0 to infinity j prime t dt. The right side, integral from 0 to infinity negative 2 e to the power of negative t squared I dt. Let's look at the right side first, because the right side equals, take the constant negative 2 and I out, so we get integral from 0 to infinity. So the e to the power of negative t squared dt, that is another I, right? So we get negative 2i squared. Look at our left side. The left side, using fundamental theorem of calculus, we get the antiderivative, which is just j of t, evaluate at infinity and 0, plug in j infinity minus j 0. When t equals infinity, you can see the top becomes e to the power of negative infinity. That's 0, right? Minus when t equals 0, so e to the power of 0, 1. So we get the integral 0 to infinity 1 over 1 plus x squared dx. You see the antiderivative is exactly the function arctan at x. So evaluate at infinity and 0. So we get negative when x equals infinity, arctan is pi over 2. When x equals 0, arctan is 0. So we get negative pi over 2. Left side equals right side. So write down. So negative 2i squared equals right side, negative pi over 2. So we get I squared equals pi over 4. Taking square root, so we get I equals square root of pi over 2. Then double it, we get our target integral square root of pi. If you like this video, please subscribe. Thank you.